I don't want to date myself, but COVID did just happen recently, and this exam, I guess, predicted that, really. It's ahead of its time. So this question is about a virus, and it increases exponentially. So it spreads exponentially at a constant rate of 5.3% each week. So n naught, so n subscript 0, we call that n naught. If you didn't know, naught means 0. Is the number of people initially diagnosed. So that's our initial condition, our initial value. And t is the number of weeks after the initial diagnosis. So the number of people infected is equal to the initial amount of people. So whenever this model started, right, the initial condition, times 1 plus the rate. So it's the 5.3% is an increase, so it's 1.053. So it increases every week by that amount. So it keeps multiplying it by that rate each week, starting from the initial amount. So for example, if time was 0, this would equal 1, and the number of people infected is the initial amount. That makes sense, right? But if we increase time, we'd expect an exponentially increased number of people infected. And so the first question is, how long will it take for the number of people diagnosed with the virus to be 3 times the number initially diagnosed? So we're looking for n, the number of people infected, or diagnosed, to be 3 times the initial amount. Right, so that's the number of people diagnosed is 3 times the initial amount. And well, we know that the number of people infected or diagnosed is equal to the initial amount times this rate increase to the power of t. And now we're solving for t, right, for time in weeks. So I can see we could divide both sides by n naught. Great. And so now we have an exponential equation. And so to get t out of the power, we can take the log of both sides. So remember, logarithms and exponential functions are inverse of each other. So we're kind of undoing the exponential. But if we take it of one side, we need to take it of both. Right? And now, using our log laws, I can bring this power to be multiplied out the front of this log. So log 3 equals t times the log of 1.053. And now we can divide both sides by log of 1.053 to get t equals log of 3 divided by log 1.053. And now it is actually good enough to just leave your answer like that. However, we can compute it. So it's just log brackets 3 all divided by log bracket 1.053 bracket, which is 21.27 weeks. Right, so to summarize that, after about 21 weeks, the number of people diagnosed with the virus will be 3 times the initial amount. Right, so every 21 weeks, the number of people diagnosed increases by a factor of 3. Now, part 2, we have a different virus, also at an exponential rate, with a constant rate of infection. which is unknown in this case. We're given that 2,500 people were initially diagnosed, and we're given after 10 weeks, the number of people diagnosed was 4,250. Right, so we're given a bit more information, but here we're actually trying to find this rate of increase. So let's just set up the problem like before. We have the number of people infected is equal to the initial amount times, now here's the tricky bit, instead of the rate, right, because it's in a percentage, it's actually 1 plus the rate divided by 100. So think back up here. The rate was 5.3%. And so to get 1.053, right, if we're increasing something by 5.3%, it's the same as multiplying it by 1 plus 5.3 divided by 100. So just something to watch out for is to convert the percentage to a decimal, and since it's increasing, we add that to 1. If it was decreasing, we'd subtract it from 1. So that's how we get this expression here. And now that's all raised to the power of t. So what we're given is the initial amount was 2,500. We're given that 4,250 people were infected when it was at 10 weeks, so to the power of 10. So now we have an equation with one unknown, so we can now solve for the rate. So let's divide both sides by 2,500. Then we can take the 10th root of both sides. Right, so that's the 10th root, as we're raising the right hand side to the power of 10, so to undo that, we'll take the 10th root, which gives us 1.0545 equals 1 plus r over 100. And just by this, we can actually see that the rate must be 5.45%, but let's just complete it. So we subtract 1 to get 0.0545, and then we times it by 100 to give us 5.45% is the rate. So to summarize this one, we were given the initial condition, and we were given a point at a certain time for a certain number of people infected, and we were able to then plug those in and solve for the rate of change.